All right. Sorry for the delay. Just about to start the main part of the course, where we talk about quantum mechanics. Can someone remind me when the first assignment is due?
Monday.
Next Monday?
Yeah, the 1st, February 1st.
Right, okay.
I thought it was the 5th, isn't it?
Yeah, it was supposed to be the 5th, right?
On Slack, I'm pretty sure it says the 5th.
Oh, well, that's nice. I'll have to double check.
Yeah, it is due February 5th. All right. Okay, so let's let me get right to it. So okay, so the main axioms of quantum mechanics. I think we've done enough classical mechanics to know, well, to be able to see the analogy, the direct analogy between the two subjects. Okay, so let me let's see. I always can't decide until the very last moment whether I should begin with an example or whether I should begin with the axioms themselves. So I can't decide pedagogically what is better than which option is best. But let me just do the axioms, and then immediately I'll do an example, and then go back to the axioms. So it'll be the best of both worlds. Okay, so number one, okay, is about what the state of a system is. Now, in classical mechanics, the state of the system is a point in phase space. Once we know the point in phase space, we can use the rest of the characteristics of the system, like the Hamiltonian function, to dictate how it should proceed in the future. Okay, so the state is a point in phase space. In this case, the state is a vector, a non-zero vector V in big V, where big V is a complex vector space. So this complex vector space, so there's two things that I want to say. So first of all, the complex vector space could be finite dimensional or it could be infinite dimensional. It depends on what system it is that we're talking about. The second thing that I want to say is that if I draw a picture of the state, here's a state. It's a vector in this case, it's a real vector space, but I'm just trying to draw the complex vector space. So we have a state. And so we might have several states. We might imagine that the system can be in this state, or in this state, or that state, and so on. So there's many possible of these non-zero vectors giving us different states. And it's going to turn out, and we're going to see that just in a few minutes, that the scaling of that state vector is not important for quantum mechanics. But right away, I want to caution. So what that means, and you're going to hear this plenty of times, is that if you take your initial state V and you scale it by 2, right, or by -1, anything non-zero, all of these different multiples of the state vector, that they all represent the same state. Okay, and this is true, and I'm going to write it down in a second, but it's a very misleading statement to make. And the reason is because if you have a pair of states, so if I was interested in the state V as well as the state W, and if I wanted to compare these two states, then it's it's useful to think about their actual vector nature, and not to forget about rescaling. I'm going to discuss this at length later, but maybe for now we'll just leave it at that. So I'll say that the two states V and V prime, which differ by a non-zero scalar, i.e. if V prime is equal to lambda V, with lambda a non-zero complex number, these are considered equivalent from the point of view of quantum mechanics. So this is mathematically speaking, this is a very well-known construction where we identify non-zero vectors when they differ by multiplication by a non-zero scalar. This is called projective geometry. So really, rather than considering vectors in this vector space, we should think of equivalence classes of vectors in the vector space. And these are sometimes called points in the projective space of the vector space.
Sorry, is the star on the C supposed to be the dual?
No, C star is just C remove 0. It's the multiplicative, it's the invertible elements of the complex numbers. Sometimes people write this as C with a cross, but it's more common to see just C star. Okay, so for today, this whole issue about rescaling the state is really not of any importance. The basic point is that states in quantum mechanics are non-zero vectors in a vector space. And right away, we see that it's a lot simpler than in classical mechanics, because in classical mechanics, the state is given by a point in the phase space, and the phase space is a nonlinear space in general. It could be like the cotangent bundle of the two-dimensional sphere, or it could be some more complicated nonlinear space. That's not the case in quantum mechanics. Okay. Number two, in order to define okay, so the next thing is about, instead of being about states, I need to talk about observables. So an observable in classical mechanics is one of the functions on phase space. So for example, when we were talking about phase space, we had certain functions like x, which was the position of the state, the position of the system. And that function took a value on the state, and we could identify, what's the value of x and what's the value of p if the system is in this particular state. We could identify its position and its momentum. Those are examples of observables. So in classical mechanics, the observables are the real functions on the phase space. And in quantum mechanics, the observables are, they're not functions, but rather they are self-adjoint operators X. And these are maps from the vector space to itself. Okay, now this is a little bit tricky, the way I said this. The reason that this is nonsensical is that the notion of self-adjoint, does not make sense in a complex vector space. You need to equip the vector space with an additional structure, which is a Hermitian inner product. V is equipped with an inner product. Okay, and this is a Hermitian inner product. Let me just make sure that what I'm going to say is consistent with my notes. So this is, for example, if you have u and v in c to the n, then the inner product of u and v is by definition u transpose bar, complex conjugate, multiplied by v. So this Hermitian inner product is linear in the second argument, and it's anti-linear or conjugate linear in the first argument, and it satisfies the condition that the inner product of u with itself should be a positive real number unless u is equal to 0, in which case it is 0. Okay, this is just a comment that I need this Hermitian inner product in order to even define self-adjoint. So that is to say, what does it mean to be self-adjoint? It means that XUV inner product is equal to UXV inner product. Okay, so this is okay for finite dimensional V. For infinite dimensional V, we're going to talk about that later. This is still true for infinite dimensions, but I need to add something in that case to this definition. Okay, so normally, just to remind you in case it's been a while since you've seen these adjointness and so on, normally if I have a linear operator, it will have an adjoint. Usually, sorry, there's always this problem of how to denote the adjoint. Oftentimes it's just with a star, which conflicts with the notion of dual. You could also use dagger. So this is the adjoint operator. And this equality defines the adjoint. The adjoint is the unique linear operator on the complex vector space for which this equation is true for all u and for all v. So this is the defining equation for the adjoint in the finite dimensional case. That this should be true for all u and v, just as a reminder. And the fact that we have this equation is telling you that x is its own adjoint. Okay, and if we use this same example, so in c to the n, x is a matrix. It's an n by n matrix. So I'll denote that by c to the n cross n. And this is an observable exactly when x conjugate transpose is equal to x. Okay, and okay. The key thing to remember, the key property of self-adjoint operators is that the eigenvalues are real. For obvious reasons. That if the conjugate transpose of x is equal to x, imagine if x is diagonal, then this would tell me that the diagonal entries of x must be real numbers. So this is the analog of real valued functions on phase space. Okay, and we're going to get to the interpretation and everything later, but I just want to make sure that the mathematical model is clear. So far, all we have is a vector space, a complex vector space, together with a Hermitian inner product, and we consider the observables to be self-adjoint operators. Okay, number 3. Let's get. So now that we have the states and the observables, and I should say among these observables, okay, just like in the case of classical mechanics where we had a special function which was defining the system in a sense. I mean, if you give me a phase space, there is no special function on it. You need to specify it for me. Then it becomes special. You need to choose the function. The function determines the time evolution of the system. So we usually, we choose one such operator, H, and call it the Hamiltonian. Okay, so now we've got our vector space, we've got our inner product, we have the notion of observables, and we have a particular observable, which is called the Hamiltonian, which also will play the role of the energy observable. Okay, now think about how classical mechanics works, right? Classical mechanics is this nice model or mechanism by which we can see the evolution of the state. And when we see that evolution, we see that whatever is supposed to be conserved is conserved. So for example, if you give me the total energy function, that function will generate a flow, and that flow will preserve the energy. So it's the same thing here. The Hamiltonian will dictate the evolution of the state. So that's the third axiom. So the state evolves in time. Time, by the way, is treated as a continuous real number, just like it is in classical mechanics. Right? So the time is not somehow embedded in this vector space or in the states or in the observables. It's separate. It's a real smooth parameter. And the state will evolve in time via the Schrodinger equation. And this Schrodinger equation is going to be the analog of the Hamilton's equation, and it is the following equation. It's d by dt of the state is h applied to the state, and we need to multiply by I, which for a reason that I'm going to explain later. And there's a conventional parameter that's introduced, h bar, Planck's constant, which is a new, it's a unit-full quantity. So from a mathematical point of view, we don't need to consider it. If we choose units appropriately, then this h bar will just be numerically 1. So it's not really that important, this h bar, for what's coming up. We can take h bar is equal to 1. But it's often useful to treat it mathematically as a parameter or auxiliary variable. We could imagine that h bar, we don't really know the value of h bar. We could imagine that it's just some additional variable, which is not involved in the dynamics or anything. It's just showing up in this equation. And so in a way, you could think that h bar gives us a parameter, gives us a family of quantum mechanics. And it's up to you to decide what value of h bar you want to choose. But for everything I'm going to say h bar, you can just take it to be equal to 1. Okay, and okay, so this equation is looks really simple. Notice about it that it's first order in time. It's basically an ordinary differential equation. Okay, so that's really similar to the Hamilton's equations, right? It's just a one time derivative is equal to some h applied to v, and right, and so yeah, and I'm going to explain this. I'm going to kind of postpone the discussion of the solution of this equation until right after I finish the axioms. But I want to say that this has a really simple solution, which is that v of t is given by u of t applied to v of 0, where this is a time-dependent linear operator, invertible linear operator. And it's actually a unitary operator. Unitary means that it actually preserves the inner product. This is the definition of a unitary operator. Okay, so, and this unitary operator has an explicit expression, and it's just e, the exponential of h. Okay, so I want, before I explain somehow all the mechanisms here of how this thing is working and the relationship to Lie groups and Lie algebras, okay, I just want to emphasize the analogy with what we did before, right? So here what we see is that we have an observable, h. That observable is occurring in the differential equation, right? The differential equation is saying that the state is changing based upon the value of this observable. So this is very similar to the Hamilton's equations, right? Where the left-hand side is time derivative and the right-hand side is the Hamiltonian vector field. Here, the Hamiltonian vector field is pointing the way towards where this thing is evolving. The point in phase space is evolving, and the tangent vector, or its velocity inside phase space, is given by the Hamiltonian vector field. The Hamiltonian vector field is determined by the observable, the Hamiltonian observable. Okay, now, and then we see that in order to obtain the flow, in order to actually find an integral curve which tells you the evolution, this is the analog. This v of t is the analog of the integral curve, right? In order to find that, we need to integrate the vector field. And the way we did that was by exponentiating it, right? And that's exactly what's happening here. We're exponentiating the Hamiltonian vector field. So maybe I should write some of these analogies. This is the analog of the integral curve, or trajectory, as I was calling it. This is the analog of Hamilton's equations. This is the analog of the Hamiltonian vector field. And this is the analog of the flow of the Hamiltonian vector field. Okay, and here you can see that this flow preserves this inner product, and yeah, yeah, it's similar to the fact that the flow that we studied in the classical mechanics was basically preserving all of the structure that we had set up up until that point. And here, this what we have so far is a vector space with an inner product, as well as this function h. And so, anyway, hopefully you can see the analogy so far. Okay, now here comes two really important axioms, the most kind of important ones. Well, maybe the least obvious ones. I don't know. Number 4. This is the measurement axiom. And I'm going to state this for finite dimensional vector spaces. And we'll return to the infinite dimensional case later on. Okay, so I'll break it down in a few steps. Number 1, the result of measuring an observable must be one of the eigenvalues of that observable. Okay, and when I say measuring, it means that you're doing some, like, you approach the system and you do some kind of manipulation on it, right? You shine a laser on it, or you hit it with a hammer, whatever. You do some kind of operation on it. Usually that operation is extremely complex. Usually it involves some kind of amplification where, for example, if you wanted to if you wanted to send an electron, if you shot a bunch of electrons at a screen and you wanted to know whether, and you wanted to detect whether there was going to be an electron coming out of a hole in the screen, right? Then you would set up some kind of large apparatus which amplifies some kind of electrical signal, so that if one electron hits, let's say, a charged plate inside your instrument, then it sets off some kind of chain reaction where there's a cascade of thousands and thousands of electrons that get released, maybe because you set up the instrument so that it was metastable, like it was kind of stable, but it was with any perturbation, maybe you would get this huge dump of charge, right? And so just the tiniest amount of charge would affect a large number of electrons. They would flow, and you would get an actual current, and that would light up a light. And then you would say, oh, I measured the presence of an electron at this position. Okay, so what I'm trying to say is that I don't want to axiomatize the actual measuring apparatus, which is a very complicated system, which is separate from the system in question. I don't want to get into that, right? So we're going to abstract it out. We're going to say that there is some kind of measurement happening, and that measurement will result in an eigenvalue. So, for example, we usually take a ruler, okay, and we look. So, usually in classical mechanics, we have a ruler, okay, which has these numbers on it, these real numbers. Okay. In quantum, okay, you have an operator, x. Okay, and then the operator, this is a picture of the complex plane. Here's 0. Okay, this operator has, and here I'll draw the real line inside the complex plane. And this operator has a spectrum. This is the set of eigenvalues. of X. And there will be some collection of points. There could be intervals. It could be the whole real line. There's all kinds of possibilities for what this spectrum could be. And these eigenvalues are the possible results of measurements. Here, these are possible results. Okay, so the type of result that you're going to get is the same. It's a real number. But the relationship between the observable and these results is a little bit more subtle. Instead of the observable being really the same as the results, because it's a function that you evaluate on the state, right? So this you could think of the ruler as being a function, right, of the state. That if the state is here, then the ruler takes a certain value on that state. Okay, so the ruler is defining a function on the state space. We could think of this as a function on the space of states or positions. Okay, in this case, we have this operator, and the operator has a spectrum, and it is the actual numerical values of the spectrum which will be the output of your measurement. Okay, and now the second part of this is that, so let P lambda be the orthogonal projection So P lambda is going to be a map from V to V. And what it's going to do is take any vector and project it orthogonally to the lambda eigenspace. Okay, then the main thing that this vector space is doing for you, right? So notice that because the possible results of the experiment are the spectrum of an operator, those are just real numbers. So, so how do you use the actual vector space and the operator? The way that, the job that does is it gives you the probability with which you will obtain these different results. So the probability well, okay, so let me phrase it this way. So if the system is in state V, the probability that measuring the lambda eigenspace of an operator, an observable X. Okay, if the system is in a state V, the probability that measuring X will yield lambda is basically given by the squared norm, like the component of the vector. If this is the vector, and if this is the lambda eigenspace, then this vector will have a component along that eigenspace, and it will have a component along other eigenspaces. So it is the length squared of the component in that eigenspace which tells you what the probability of obtaining lambda is. So the probability that measuring X will yield lambda is P lambda V. So we take the component of V in that eigenspace and we measure its squared norm using the Hermitian inner product. And of course, you should remember that if I rescale the state, I shouldn't get any different physics. So this really should be modified. And in addition, this component might be gigantic, right? I mean, the vector could be huge, and then the projection could be huge. So this cannot possibly be a probability. The probability has to be less than 1. So for both those reasons, it's clear I should divide by v squared. And if I rewrite this, I could write it in the following way. So this is a kind of clever way that it's usually written in. It's written like this: v p lambda v divided by vv. Okay, so what's going on here is that once I've projected out this component of v, when I take the inner product against v, it will only see the component of v which is in the lambda eigenspace. The rest of it will be orthogonal to that, and so I don't need to put a pv here. It's just easier to just put a single p, and that will do the job here. So this thing here, this is equal to pv. Okay. So the state, right? When you have the state and you have the observable, quantum mechanics is giving you a mechanism for defining a probability distribution, right? It's saying the observable has various different values in the spectrum, and the state has components. It has a certain component in every possible measurement outcome. Okay, and depending on the size of that component, that will determine the probability that you'll get that measurement. So essentially, what it's really doing is it's giving you a probability distribution on the spectrum of the operator. So each state gives a probability distribution so a state gives a probability distribution on the spectrum of x for each operator, for each observable x. So just summarizing this, I'm restating it. This might be a more confusing way of saying it, but it's not difficult to see that it means the same thing. So, or at least it's an outcome of this point. So just to review, you have a state. It's a vector in the vector space, a non-zero vector in the vector space. Now, whatever observable you're interested in, that observable will have eigenvalues, eigenspaces, and that state will decompose into pieces, into different eigenspaces. And those pieces will have different lengths, length squared. And the ratio of all those length squared determines the probabilities. And that will be true for position, for momentum, for energy, you name it. Okay. For each operator, there will be a different decomposition of the same vector space into eigenspaces, and the relative sizes squared of the components of the vector in the different eigenspaces, that will determine the probability distribution that the energy will be this or that, or that the position will be this or that, and so on. Okay, and then there's a third part of this axiom, which has to do with the fact that the measurement process is a somewhat undefined black box process. We don't want to specify what the measurement system is, what the apparatus is. Whatever it is, it's produced somewhere else. It's brought next to our system, and it's made to interact in some unspecified way, right? And it's designed in a certain way. And what these measurement things do is that they don't just spit out an eigenvalue. They actually take your state and project the state to that eigenspace. So they literally change the state when they measure. Measuring the observable x projects the state to the result, to the so I wanted to phrase it in a slightly different way, but I'll put it this way. So after measuring x and obtaining one of its eigenvalues, lambda, the state is p lambda v. So it's changed to p lambda v. This is sometimes called the problem, the measurement problem. And it's often referred to as wave function collapse. Okay, so somehow the idea is that you see here the way that the system evolves is by this equation, the Schrodinger equation. Okay, and this evolution is unitary, which means that if you evolve a state, you will not be changing its length. It's basically like a rotation. However, if you measure the state, okay, you're doing something that is not quite kosher because you are bringing a second system into interaction with your system, and so the system is not closed temporarily. It's getting interactions from the outside, and the evolution of the system is no longer, during that measurement process, is no longer evolving according to Schrodinger's equation. During that period, something is happening which is unspecified, but at the end of that process, the state will be this one. It will be projection onto the lambda eigen space. And you can see right away that this is only going to be, this will not preserve length. So it will, it's only projecting to one of its components. So it's very different from a unitary evolution. Okay, and the last axiom is that in classical mechanics, when we have two systems given by two phase spaces, phase space M1, phase space M2, then the phase space of the joint system is described by telling me what the state of the first is and what the state of the second system is. And so it's giving me an ordered pair of points, x, y, where x is in M1 and y is in M2, right? So we need an ordered pair of points in each of the classical phase spaces in order to describe the joint system, the union of the two systems. But in quantum mechanics, this is different. Combining the combination V1 combining one quantum system with a second quantum system yields the tensor product of the two vector spaces. And the first thing that I'll do on Friday is to discuss, well, one of the things we'll do on Friday is review the tensor product, just in case people are not familiar with it. And the inner product, the inner products can be also tensored. And the Hamiltonian operator can be combined by adding them together. Okay. And the thing I want to say before we stop is that this thing has the dimension equal to the dimension of V1 cross, multiplied by the dimension of V2. Okay, so before, when we took two phase spaces and we took their Cartesian product, the dimensions add, but here the dimensions multiply. So what that means is that the dimension of the vector space for any reasonable system of n particles is going to be gigantic, huge. Okay, in comparison with the classical phase space. So for example, Google built a rudimentary quantum computer which had, I forget how many it was something like 30, it was maybe 15 qubits or 20 qubits, I can't recall. Each qubit has a state in a two-dimensional vector space over the complex numbers. And so they were dealing with a 2 to the 15 dimensional vector space. They constructed a quantum mechanical state space of very high dimension. Well, actually, it wasn't that high, but it was very high in comparison with our usual spaces that we're used to. Okay, and the state was basically moving around in that gigantic vector space. And as they were doing computations, that vector was basically being made to move, right? And being rotated and moved and so on. And then at the end, you would apply a measurement, and then you would have this wave function collapse. You would get one of, however many eigenvalues there are. One of them would be the output of the measurement. Okay, so this is the kind of this is the challenge, is that you want to set up your vector space, you want to have your state, you want to move it around, do some kind of computation, right? Just like an abacus where you move these beads around to do a computation, except that now you're moving a vector in a very high dimensional space. And then after all of that is done, at the end of the algorithm, you measure, you apply this axiom, and you're going to get a certain result with a certain probability. And if you redo the experiment, then maybe you can get a sense of this probability distribution and so on. So anyway, I just wanted to give that's it. This is the axioms of quantum mechanics, basically. So you can kind of see that it's, in a way, it's simpler than classical mechanics. There's no phase space, no nonlinear spaces. There's no vector field that need to be integrated. What you have are operators, linear operators, which have eigenvalues and so on. So it's basically just linear algebra. That's what quantum mechanics really is. And neural networks are also linear algebra, roughly speaking. And so you could make an argument that neural networks are, in some way, very much analogous to quantum systems. It's not exactly right, because they use, for people who know about neural networks, it's not purely linear. They have some nonlinear components that they use. Okay, everyone, it's office hours. We've bled into office hours. I'm sorry. Questions we can have questions for an hour now. I didn't want to take questions because it's important. This is like the axioms of quantum mechanics. It's like, this is literally the tablets, that Moses got from the mountain. it's the commandments. You can't interrupt with such a thing.
Professor,
Yeah,
I have a question about the second axiom of quantum mechanics.
yeah.
This is more of like a notation thing, but I noticed that you used bar star for the transpose complex conjugate, but also used the dagger symbol on the to denote the adjoint of T. Is there?
Yeah, this is just the adjoint.
Oh, okay. So there's no.
Sometimes it's also written as a dual or as a star, but that physicists will often use the star to mean complex conjugate transpose. But when you learn vector spaces and in many other scenarios in mathematics, the star denotes just the dual which doesn't need any inner product. It's just the dual operator on the dual vector space.
Right.
So yeah, hopefully there's no confusion. In quantum mechanics, the operators are going to be self-adjoint.
All right. Thank you.
You're welcome.
I have a question, actually. I think it was about the probability axiom for the measurement.
Okay,
Like, if we're identifying all the vectors that are scaled from each other,
Yeah.
like, why do we bother normalizing the probability if we could just choose the representative of the class that is already normalized? You know what I mean? Like, why don't we just talk about that element instead of these like elements?
It's not that you don't. It's you certainly can, right? If you want to, you may decide that you want to describe your state by a unit vector. So if you insist that you will always describe your state as a unit vector, a vector with norm squared equal to 1, okay, then this denominator will not be there, and so it'll be easy to compute this, right? But the problem is that when you do a measurement, that unit vector is going to be projected to one of its eigenspaces, to one of the eigenspaces of the operator, and that result will not be a unit vector, and then you're going to have to renormalize it. And so if you are obsessed with having unit vectors all the time, you're always going to have to be, renormalizing the state vector all the time, blah, 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 right? So it's convenient to write the formalism in a way that doesn't require normalization, just so that you can skip that step. That's all. The other problem with normalization is that if you take a vector and you multiply it by e to the I theta, that will also be a unit vector. It will have norm squared equal to 1. So e to the I theta for theta real. This will have the same norm squared. So you should not think that normalizing your vector is picking a unique representative from the class. It doesn't. So, even if you normalize it by dividing by its norms, by the square root of its norm squared, you still don't get a unique representative for the state. And it's not helpful. You see, like from classical mechanics, we like the idea that there's a unique point which describes the state. But this, in the vector space, it's not useful to think that way. Now, okay, I mean, what you could do is you could take, and we're going to do this later, you could take the entire vector space and just use an equivalence relation that says that V and V prime are equivalent when they're related by multiplication by lambda, non-zero complex number, and that will quotient the vector space to produce what's called a projective space, which is not a vector space. And so you could say that the states are actually points in that projective space, and that these points are evolving by moving around. So that is another way of thinking about quantum mechanics too. It's equivalent to this one. But in practice, it's just way easier to deal with the vector space and to deal with unnormalized states. It's just a practicality.
Yeah, okay, that makes sense. Thanks.
Okay.
Measurements happen instantaneously in time in this model.
Yeah,
Okay.
that's right. Yeah, that's right. So the state basically evolves according to a rotational evolution, a nice smooth differential equation, until measurement, in which, and that at that point there's a discontinuous switch from whatever the state was to whatever the measurement dictates. The measurement could give any of the eigenvalues, and so the measurement result, the state after measurement might be in any of its eigenspaces, any of the operator's eigenspace. You don't know which one it will be in, but it will select one at random, drawn from the probability distribution on the spectrum. So it's basically going to, it's the state, the particle is basically going to say, okay, what are they trying to measure? They're trying to measure my position. Okay, position operator. What are the eigenspaces? Okay, so these are the eigenspaces for the position operator. I have a component in each one of those. Therefore, the probability that I'm going to go onto each of these subspaces is dictated. So I'm just going to now randomly choose. And then there's an instantaneous choice, and it just goes into that subspace. So that's why people are not comfortable. I mean, this is this measurement axiom is the one that people never liked, but it really and a lot of work has been done in the last 20 years about making more complicated mathematical models that explain why there is this. Why this measure, how the measurement process works. But these models, these sophisticated models, they lead to this axiom. They do not explain, they do not give a deterministic version of this process. It's still non-deterministic. It's still a probabilistic passage after measurement. It's probabilistic. It's not deterministic. And the more sophisticated models that microscopically describe the measurement axiom, what do? They actually just result in the measurement axiom. They result in this non-deterministic axiom. So in a way, it is a good black boxing. It seems to be a true fact that is not an approximation of the underlying. It's not an approximation of the result of measurement. It's a simple. It's a correct simplification of the measurement process, which we leave as a black box. I'm expecting that what I just said is going to be confusing to people. You can ask. Don't feel like you should. I'm not expecting you to understand what I'm saying. I'm expecting you to ask questions to like make sure. I'm basically telling you the things that you're supposed to understand. It doesn't mean that you should understand them based on what I'm saying. You might have to question me. So. You can kind of imagine, like you can kind of imagine that inside the state, the system is undergoing some kind of highly complicated dynamics, which you can kind of imagine that maybe it is maybe there is some kind of underlying mechanism that is driving the evolution of the state under measurement. But but that mechanism, that that deterministic mechanism, okay, is completely inaccessible. It can never be accessed by the outside. So, you know, you're allowed to pretend that there is something deterministic going on as long as you will never be able to see it ever. So that's why we eliminate it by Occam's razor. There is no possibility that we can describe this measurement process in a deterministic fashion. So that's why it's a probabilistic theory at its heart. And you know, yeah. Sorry, go ahead. I should stop talking.
Oh, sorry. I just have it's probably a pretty simple question, but for number 2, the
Yeah.
second axiom, I'm a little like basically like what is, when we talk about observables, I'm just trying to like draw the connection between what it means in classical and quantum mechanics. Like I'm just trying to make that connection.
So these observables in classical mechanics, so in classical, these are real valued functions of the states. So remember that in classical mechanics, we had the XP space, and we said that the state of the system is given by a point in that manifold. Okay, and there's various functions defined on this space. For example, X is a function defined on this space, and we can evaluate the X function at this point, and we'll get 3.5 because the particle is at the position 3.5. The particle could be in a different state. It could be over here, in which case the X variable would have, the X function would have value -3. Okay, so observables are functions on the state space. These functions can be evaluated on the states and giving numbers. In quantum mechanics, the observables are operators, and the operators they are not evaluated on the state, but rather the operator has eigenvalues. It has a spectrum. And this spectrum are the possible results of measurement. And so we can't say that a state has the value of this observable X, which is 3.5. That doesn't make any sense. The state will have components in the various eigenspaces of X. Okay, and those components, depending on how big the components are, they will tell you the probability that the measurement of X on the state will be the various eigenvalues.
Okay, yeah, thank you. That makes sense.
Does that make sense, or is it confusing?
Yeah, no, I kind of get that. I'll probably think of it a bit more, but I get
Okay.
it. Yeah, on the way.
Yeah. Yeah.
Classical mechanics should emerge from quantum mechanics, right? If you take a large enough system or a macroscopic system with a lot of complicated behavior. So is there an explanation for where the linearity goes when you like zoom out to the classical system, why it disappears?
Yeah, that's a good question. So what is a classical observable? What is the set of, well, okay, yeah. Yeah. So okay, yeah. So to answer your question, the simplest answer is that yeah, the simplest answer is that this vector space of states. So, okay, what you said is true, that a quantum mechanical system in a certain limit, and actually the limit is as h bar goes to 0, it limits in a complicated way to a classical system, okay? But in the analogy that I gave, it's not that the analogous things limit to the analogous things, okay? It's not true that the vector space limits to the phase space. It doesn't go directly in that way. Okay? You should think that from you could think of it that from the vector space of states and the result and the rest of the structure of the quantum mechanical system, we can construct a sequence of spaces which limits to the phase space. You can somehow think of it that way, or you could do it the other way around. You could say that if I want to describe the phase space, one way of actually maybe a good way of saying it is like this. So the question that you're asking is really the heart of the subject, which is called geometric quantization. It has to do with what's the relationship between the phase space and the quantum mechanical system that might be associated to it. So you could think of it that when you're describing a classical system, there's a configuration space. That configuration space is some nonlinear space. Like it could be that the particle is moving along a circle, or it's moving along some complicated space. That space is the configuration space, and it's a nonlinear space. It's not a vector space. However, if we consider the space of complex valued functions on that space, that will be an infinite dimensional vector space. Okay, and so you might say that for every classical space, configuration space, I can construct an infinite dimensional complex vector space by simply taking functions on it. And that is one of the main kind of elementary first steps of geometric quantization. You produce the quantum mechanical state space from the functions on the configuration space. And these functions are called wave functions, but they're just vectors in the quantum mechanical state space. So that's one possible answer to your question. But in truth, okay, there might be many classical there might be many ways of obtaining a classical system at the limit of as h bar goes to 0. So it really depends on your it really depends on the particular formalism that you're working in. There is not a canonical correspondence between quantum mechanical systems and classical mechanical systems. They're not in one-to-one correspondence. And in particular, there will be quantum mechanical systems which have no classical counterpart, and there will be the reverse as well. Later on, we're going to study this in a bit more detail. We're going to study the sense in which quantum mechanics, at least in some cases, can be thought of as a deformation of classical mechanics. A deformation in the technical sense of deformation theory. And this is what's called deformation quantization. It's one of the famous approaches to quantization. It's like imagining that you have a family of algebras where at h bar, which is parametrized by h bar, and at h bar is equal to 0, it's a commutative algebra, and it corresponds to our usual space of functions on phase space. but then for h bar non-zero, it becomes a non-commutative algebra. And so you can kind of algebraically, it makes sense that you can have a non-commutative algebra, which is a deformation of a commutative one. And yeah, you can see here also that, I mean, I haven't discussed it yet, but I'll discuss it on Friday, that because observables are given by these operators, it's clear. Well, there's two sources of kind of weirdness coming from this measurement axiom and from this observables axiom. So one of them is that observables are operators, and so they don't commute. They're matrices, basically. Whereas in classical mechanics, X and P, they commute. We typically make polynomial expressions of X and P to produce our Hamiltonian function. And it's a commutative algebra of observables. In quantum mechanics, it's very far from being the case. These are like n by n matrices or infinite by infinite matrices. So they don't commute. But it's even worse than that, because in the measurement axiom, what you see is that after you measure one of these things, the state gets projected into one of the eigenstates. So if I measure X, like position, and then I measure momentum, at the end of that sequence of measurements, I'm going to be in a momentum eigenstate. But if I did the measurement in the reverse order, I would have to be in a position eigenstate. And there's no guarantee that this state can be a eigenstate for both operators. The operators might be so different that they don't share any eigenvectors. And so there is this very strange fact that if you measure the position of a particle and then you measure its momentum, or if you measure the momentum first and then the position, you're going to get different results for both quantities. So yeah.
Professor, I have a question regarding related the theory to the real physical world. So I'm not sure if my understanding is correct. So the observables corresponding to some devices in the real world, right? Which you can measure the.
Sorry, you're going too fast. Just repeat the question.
The observables is an abstract of the some large devices in physical world.
No. The observables are what they sound like. They are observables. So position is a quantity, right, which we can observe.
But I mean, in the real world, if you want to measure.
No, in the real world, okay, yes. Okay, the person in the room has a position, yes. Right? Okay, so I'm telling you, I'm in my room right now, right? I have a position. The position, there is a position observable. There is a momentum observable. My momentum is 0 right now because I'm not moving. Okay, but you're not measuring. You didn't measure anything in the real world. You didn't measure anything yet.
Okay.
But there is an observable quantity, which is the position. There is a function on my room. It has values, different values at all different points. That function is the observable position.
I see. Then when you say the probability that measuring X, then you are using some devices to measure.
There are three things. Okay, so there's two things. There's the observable, which is the quantity which can be measured, and then there's the measurement event.
Yes.
Okay. When you do a measurement event, there is a drastic thing that happens. The state is projected into one of the eigenstates automatically, and the result of the measurement in the real world will be the eigenstate, will be the eigenvector. Will be the eigenvalue. Will be the eigenvalue. So, for example, you don't know where I am in my room, but if you ordered a measurement, what would happen is that I would respond with a number, a real number, which told you my position. Okay. And I would be projected onto the eigenstate of position operator. I would be in that position after the measurement. But that is a probabilistic result. If you repeated the experiment again, okay, if you reset everything, then and you repeated the experiment, the position might be measured to be different, and that has a certain probability associated to it. If you reset the state exactly as it was before, okay, the measurement would give you a different result. It would give you, a different result with a certain probability. So if you apply a measurement to a state, the result is not determined. It's only probabilistically determined.
I see. So like only like the measurement, like the measurement stuff only corresponds to some real world stuff, right? Only like the measure events happening, then you like have some devices to measure a system.
No, so I'm going to say something now which is important. Okay,
Okay.
You are wrong. You are wrong about that. Okay,
Yes.
so don't. I can tell that you want to be right, but you're not right. Okay.
Okay.
So what you have to do is look. You have to try to train yourself away from that. So when we evolve the state, okay, there's a state which is a vector in the vector space, and that state is evolving. It's moving around. Okay, it's evolving according to one of these observables, right? So there's an energy observable, okay, the energy operator. That energy operator occurs here inside the differential equation, and it causes the state to move. Okay, this thing apparently is happening in the real world. There's no measurement happening here. Okay, the state of the system is moving, just like in the harmonic oscillator. The particle the spring was moving back and forth. Okay, and what you were doing, if I tell you the spring is moving, it's according to this differential equation, then you're going to tell me, well, I don't believe you. Let me see, right? So then I'm going to show you the spring, and it's going to be moving like this, and you're going to observe. You're going to make all these measurements, measure at every single time 1,000 times, and you're going to verify that this motion in the differential equation is happening in the real world. Okay.
Yes.
So right. Okay. So that's how you verified somehow that it's happening in the real world. Now in quantum mechanics, this state is moving according to this unitary evolution. Okay. And if we measure it, then there's there's this process that happens, and that measurement will happen with a certain probability. Okay, but so you might say, well, how do you know that before I measured, or between two measurements, how do you know that the system is evolving according to this unitary evolution of the vector inside this 50-dimensional vector space? How do you know that it's really doing that? Well, the answer to that is, well, okay, if I evolve it for a few seconds, that vector will change, and the components of that vector in the different eigenspaces will change, and therefore the probabilities that I will measure the vector, measure that state, that the measurement outcome will be a certain probability distribution will change. The probability distribution of your experiment will change. Okay, and that's how we verify that this vector really is moving. The components of the vector in the different eigenspaces are really changing, and the probability distribution is changing with time.
Okay.
Okay. So that evolution that's happening, it is somehow a real evolution, because it has many, many real world consequences. It affects all of the future measurements in a very complicated way. Does that make sense? So it seems crazy,
Yes.
but what the Google engineers are doing is they are literally tracking and predicting and applying linear operators to a vector in like 100-dimensional, 1,000-dimensional space, right? They're moving that vector around. doing a bunch of complicated calculations, and they are being very, very careful not to measure it at all until the end, because they don't want to ruin all of the very subtle rotations that they're doing in different directions in this high dimensional space. They want to make sure that they are doing all these rotations and they don't want to observe that thing. Because if as soon as they observe it, they're going to lose all their work, because it's going to get projected to an eigenspace with a certain probability and everything's going to get ruined.
I mean to think about this. I need to think about this.
Okay.
Yeah. Thank you for explanation.
No problem.
When we move to the infinite dimensional setting, does the spectral measure essentially correspond to what we're describing here? Is
Does
that
the what?
to
Does the
consider?
what? Does the what? I didn't hear what you said.
Sorry, can you hear me now?
Yes.
In the infinite dimensional setting, does the spectral measure of
Why are you asking me about a spectral measure?
Is that, well, if there's infinitely many eigenspaces, then the definition that we have here for the probability after measurement doesn't really make sense.
Right.
So there should be a corresponding probability measure on the spectrum of your operator.
Yeah, there's going to be a probability measure on the spectrum. Yeah, correct.
Is that measure the spectral measure that you get from the spectral theorem?
Yes.
Okay.
Yeah.
That makes sense.
Yeah, it's giving every operator, every observable gives a probability distribution on the spectrum of that operator. And excuse me, sorry. Every operator has a spectrum, okay? And every vector determines a probability distribution on that spectrum. As the vector changes, so does the probability distribution, because the components of the vector in the different eigenspaces changes. So you have to be careful about, what are your ingredients. If you only have an operator, right, then what you'll have is a spectrum, and you're going to have you're going to have a decomposition of the vector space according to the spectrum, and you'll have what the spectral theorem gives you, which is a decomposition of the operator in terms of that, in terms of those eigenspaces. But in order to get the probability distribution, you need to know what your state is. So, for example, if the state happened to be an eigenstate, right, then that means that the probability of being in any other eigenstate is 0, and so the probability distribution is exactly 1. It's fully weighted on a single point in the spectrum. If it happens to be an eigenstate, then it will be like a delta function probability distribution supported at a single point. So it's very funny that when you start your system, it could in principle be in any state. It's in a combination of states. It has a combination of different values of the observable. But as soon as you do a measurement, this probability distribution basically gets squashed into a single point in the spectrum, and it becomes a delta function, and it tells you that after measurement, it's definitely in this state. So you could think in terms of probability distributions, but that is missing some of the point. So the probability approach is not quite right, because for the simple reason that probabilities are given by the norm squared of things, you see. So you are it's important that there's the quantum world, which is happening at the level of the vector space and the operators. Okay, and then there's the probabilistic world, which involves taking norms of things, and so you are kind of forgetting some information. So, for example, if I was to yeah, anyway, I don't want to get into any more detail until later. Hopefully that is helpful. Yeah, I'm gonna have to do more about tensor products. That's all right.
Why? I see mathematically why we would care about infinite dimensional systems, but if this is really rooted in trying to model some sort of physical system, and each qubit is, whatever, a one-dimensional complex system, then you're never actually going to reach infinite dimensions, regardless of how big your computer gets or how big your system gets. So why consider infinite dimensional spaces?
Well, what are the allowed frequencies of light according to you?
I know next to nothing about physics.
I'm asking you how many colors of light are there?
Oh, sure, a spectrum of them.
But how many? You just said that there's finitely many, so how many? How many colors?
Yeah, okay.
So we don't have any evidence that there are finitely many colors. We don't have any evidence at all that there are finitely many possible positions in three-dimensional space.
But that's different, because sure, infinitely many positions in three space, but you're still three-dimensional.
Each position is a possible outcome of an operator. The position operator has a spectrum given by the real line, all possible positions. There are three position operators, x, y, and z, and each of them has a spectrum, which is the real line, the continuum. That means that the vector space of states is
Infinite, okay.
Is highly infinite dimensional.
Okay.
So if you believe that space is discretized, that energy is discretized, that light is discretized, that everything is discretized, okay, then you could get away with a finite dimensional vector space. Now, I personally don't, I don't know. I'm agnostic as to whether the dimension of physical Hilbert space is infinite or finite. But one thing's for sure, physicists do not believe that space is quantized, nor do they believe that there's any disallowed frequency of light.
Okay. And then, so I'm guessing when we do move to the infinite dimensional setting, you'll want to be dealing with complete spaces, Hilbert spaces.
Why? Why are you insisting on bringing in concepts which haven't talked about yet? I'm just curious. Why is that? I'm always suspicious when people bring up these topics. What is the point of completeness in the discussion that we've been having? Sorry, I'm giving you a hard time, but
No, it's fair. Well, okay, two things. First of all, having a mathematical background forces me to ask these anticipating questions.
No, it doesn't force you to do anything. You're asking them because you want to.
Yeah, exactly.
So what is the role of completeness here?
Well, let's return to the spectrum of light. You could say, sure, there's infinitely many colors of light, but is there one color missing in the middle of your spectrum or not? And if you do accept completeness, then you would say no, and then that would make sense.
Why? Why is that?
Well, if it's not complete, then you have a sequence converging to your missing spectrum, missing color, rather.
No, it's not, the vector space is not the real line. The vector space,
It's more of an analogy than a.
the vector space is a sum of one-dimensional spaces, one for every real number.
Maybe it's best if I just wait and see.
So we do usually deal with complete spaces, not always. Sometimes you can deal with incomplete spaces. Often it is taken to be complete, but it is not. I mean, completeness is used more or less for mathematical convenience. Really, it's not.
I guess that's a better motivation for the question. The reason I would care about completeness would be that you would then have tools that you can apply that are much more useful, or much more.
Well, yeah. I mean, completeness just ensures simplicity. So if you have simple problems to solve, then you can deal with complete, a complete Hilbert space. But it's not. The central ideas of quantum mechanics are not concentrated in these issues of completeness. Let's put it that way. That's a secondary mathematical issue. So it's not to do with the relationship between the continuum and the quantum system. That type of completeness is different. You can imagine that you have a sequence of quantum systems which converge in some sense to a classical system, or which approximate it. And that would be a form of completeness, where you would have a sequence of quantum systems which converge in some sense to the classical system. But in terms of like what mathematical model you use for a fixed system, like what we're going to study later, we're going to study the hydrogen atom, right? And in the hydrogen atom, the Hilbert space is the L2 complex valued functions on R3. So we consider all complex valued functions of three-dimensional space, and we complete it with respect to the norm. Which the norm is just the L2 norm, the integral over all of R3 of the squared norm of the function. So yeah, for example, like if let me put it to you a different way, right? So if you have a vector space which is not complete, okay, and then you cannot go to a physicist and say, well, you're doing physics in this vector space, is it complete or not, right? Is the vector space complete or not? The reason why this is not a very good question is clear even from the mathematical point of view, because in mathematics we know that given this vector space, there's a canonical completion. So that means that going from the vector space to its completion is no additional information. It requires no extra information. It's a purely formal step, right? So in other words, anything that you can do with the completion, you can do it without the completion. So it's not an important idea in that sense. You know what I mean? Like, of course, it's an important idea because you can't prove all these various theorems without assuming that you're in a complete vector space. But from a practical point of view,
you're not
the completion is nothing special. The completion is a formal extension of the space.
Okay, that makes a lot of sense.
Yeah. Okay. Any more down-to-earth questions? Oh, there's a chat with a bunch of stuff. Okay, one second. There's people talking about measurement schemes and so on. Maybe they shouldn't be taking this class. Maybe they already know quantum mechanics. We'll see. We'll see what happens at the assignment. Let's see who else. Okay, if there's no more questions, I'm going to sign off. Have a good rest of the week, but I'll see you on Friday.
Thank you.
Okay, see you later.
See you. Thanks.
You're welcome. Bye-bye.